Hello, let's finish your 6.8. Let's do the second part of our lecture. Now I'm sharing my screen with you and I'll discuss the rest of your lecture. In previous video, I explained two types of indeterminate form of limits, which was 0 over 0, infinity over infinity. And the second one was the product, indeterminate product, which was 0 times infinity. Now, let's do number 3, which is or type 3. In type 3, we are discussing indeterminate differences. Look, if we have f of x, the limit of f of x as x approaching to a, and it gives you infinity, and the limit of g of x as x approaching to a gives you also infinity, then if you have the limit of f of x minus g of x as x approaching to a, definitely it gives you infinity minus infinity, which we call it the indeterminate form of the indeterminate differences, correct? How to deal with these types of limit? When you plug in the number, it gives you infinity minus infinity. How to deal with these problems? I'll put a kind of short note here. Follow these, one of these. You can apply one of these and you can change it again to 0 over 0 or infinity over infinity, correct? Sometimes use common denominator. Or sometimes rationalization. Or you can do factoring. Factoring out common factor. Why you do one of these? To get 0 over 0 or infinity over infinity. Some professors, they just explain this part as do some algebra to get a quotient, which is true. Which type of algebra you need? When I'm telling you use common denominator, it's algebra. Or when I do rationalization, it means rationalize the denominator, that process, correct? It gives you a quotient. Or when I'm telling you factoring out common factor, basically it gives you a quotient, right? Some people say in this way that use algebra to get a quotient. Or I give you like at least 3 different methods that how to get a common quotient, right? Now, let's do an example. I'll explain an example for you. Compute. Limit of as x approaching to pi over 2 from left, secant x minus tan x. Secant means 1 over cosine. You have to plug in first, right? 1 over cosine. Cosine of pi over 2 is, when your cosine of pi over 2 is 0, correct? 1 over 0 gives you here infinity. Minus tan of pi over 2 At pi over 2, if you remember the graph of tangent, this is pi over 2. When you are approaching from the left, the graph goes to infinity, right? This is the graph of tangent. It means you end up with infinity minus infinity. Now, as soon as I plug in and I see I end up with indeterminate difference, then I try to change this one to a quotient. How? Use algebra. Use, for example, common denominator, correct? Look, can I write limit of x approaching to pi over 2 from the left as a, instead of secant x, can I write 1 over cosine x? Minus, instead of tangent x, can I write sine x over cosine x? Now, use the common denominator method. You see, here you have cosine x, here you have cosine x. Write it as a one fraction or write it as a quotient, right? You can write this one as a limit of x approaching to pi over 2 from the left, 1 minus sine x over cosine x. Correct? Now, if you plug in pi over 2, sine of pi over 2 is 1. 1 minus 1 gives you 0. And cosine of pi over 2 is 0. You end up with 0 over 0. As soon as you end up to 0 over 0 or infinity over infinity, apply the L'Hopital's rule. Then you can rewrite this one as a limit x approaching to pi over 2 from the left. The derivative of numerator, the derivative of 1 is 0 minus the derivative of sine x is cosine x. The derivative of cosine x gives you negative sine x. Simplify a little bit. Limit x approaching to pi over 2 from the left, negative cosine x over negative sine x. Or you can say this one as a limit x approaching to pi over 2 from the left, positive cosine x over sine x. And if you plug in here pi over 2, cosine of pi over 2 is cosine x over sine x, you know, it gives you cotangent x, correct? And as x approaching to pi over 2 and cotangent, it becomes what? The graph goes to 0. Or other way, cosine of pi over 2 is 0. And sine of pi over 2 is 1. 0 over 1 gives you what? 0, correct? Which way you go, both way is the same. Example number 2. Limit one over x minus 1 over 1 minus cosine x as x approaching to 0 from the right. If you plug in 0, the first fraction gives you infinity. And the second fraction, cosine of 0 is 1. 1 minus 1, 0. It means you end up again with infinity. Now what you do, you have to find common denominator. To find common denominator, limit x approaching to 0 from right. You have to multiply your first fraction with the second denominator. It means 1 over x times multiply the top and bottom with this denominator, which is 1 minus cosine x. Here, 1 minus cosine x. Minus, here you have to multiply it with the x. 1 over 1 minus cosine x, multiply top and bottom with with x, right? To get common denominator. Now, denominators are the same, just simplify the top. You can write this one as a limit of x approaching to 0 from the right. One of the denominators, which is x parentheses 1 minus cosine x. And the top, you end up with what? 1 minus cosine x minus x. Before plug in, you can distribute this x to denominator, or if you wish to check, plug in 0, first check, then do that step. Let's first check, let's plug in 0. If you plug in 0 here, it gives you 1 minus cosine of 0 is 1, correct? And minus what? 0 over 0 times this parentheses gives you 0. 1 minus 1 is 0. Again, you see you end up with 0 over 0. Then you have to apply again the L'Hopital's rule. But before that, I want to distribute this x here. You can reuse the product rule right now, or the easier way is to first distribute. You may again end up to use the product rule in the denominator. Limit of x approaching to 0 from the right, keep the numerator up 1 minus cosine x minus x over distribute. It gives you x minus x cosine x. Here is the part when you do the L'Hopital's rule, you have to apply the product rule here, correct? Then L'Hopital's rule, limit, the derivative of numerator, the derivative of 1 is 0 minus the derivative of cosine x gives you negative sine x, and the derivative of x is 1. Over derivative of x is 1 minus, here product rule, f prime g, it means 1 times cosine x plus f g prime, it means x times negative sine x, correct? Simplify the denominator, limit, and the top, negative sine x gives you positive sine x minus 1 over 1 minus cosine x, negative times negative gives you positive, correct? Positive x sine x as x approaching to 0 from the right. Now plug in to check. Sine of 0, sine of 0 is 0. It gives you 0 minus 1 over 1 minus cosine of 0 is 1 plus 0 times sine x gives you 0, correct? It means you end up with negative 1 over 0, which gives you what? Negative infinity final answer. This was the third type of indeterminate form of limits. Now, type 4. Indeterminate powers. Look, if I have the limit of f of x to the power of g of x as x approaching to a, three things can happen, three forms of them we will study here. Number one, if limit of f of x as x approaching to a gives you 0, and limit of g of x as x approaching to a gives you also 0, then the limit of f of x to the power of g of x, the limit of f of x to the power of g of x as x approaching to a will gives you 0 over 0. 0 to the power of 0, sorry, not 0 over 0, 0 to the power of 0. Everyone knows 1 to the power of 0 is 1. Any number to power of 0 is 1. But what is 0 to the power of 0? Don't do that mistake to say, oh, 0 to the power of 0 is also 1. No. 0 to the power of 0, we don't know. That's why it's one of the indeterminate forms, correct? Number two, it can happen like this. If the limit of f of x as x approaching to a gives you, let's say, infinity, and the limit of g of x as x approaching to a gives you 0, then the limit of f of x to the power of g of x as x approaching to a will gives you infinity to the power of 0, which is the second form of powers, indeterminate powers. Number three, if the limit of f of x as x approaching to a gives you 1, and the limit of g of x as x approaching to a gives you infinity, then the limit of f of x to the power of g of x as x approaching to a will gives you 1 to the power of infinity. Or in a simple language, 0 to the power of 0, infinity to the power of 0, 1 to the power of infinity. These are the indeterminate powers. If you end up with these types, how to deal with, to simplify and find the limit, I'll give you a rule. If you have, for example, f of x to the power of g of x, correct? Usually in this method, we use the technique of logarithmic derivatives, but a little bit different, not too much that way. Look, you remember from algebra that if you have 2, instead of 2, you can write this one as a e to the power of ln 2. Because e to the power of ln 2 gives you back 2, correct? Now, if I have f of x to the power of g of x, I can write f of x to the power of g of x as a e to the power of ln of f of x to the power of g of x. And based on the logarithmic rules, hopefully you will remember that you can bring the exponent to the front, right? It means you can write this one as a e to the power of g of x ln f of x. Using this method, you can solve or find those indeterminate powers. Now, I'll start with few examples. I'll show it for you how to use this method to find those types of limits, correct? Example number 1. Limit of x to the power of x as x approaching to 0. If you plug in immediately from the right, if you plug in immediately 0 here, it gives you 0 to the power of 0. Now, how to deal with this problem? I'm using the ln or the e method. Instead of x to the power of x, I can write limit e to the power of ln x to the power of x is still your x is approaching to 0 from the right. Focus here. Now I'll bring the x to the front. Then I can write limit as x approaching to 0 from the right, e to the power of x ln x. If you remember from Calc 1, instead of limit e, even you can write this one as a e to the power of limit of x approaching to 0 from the right, x ln x. You can move the limit in the top. In your book, in some classes, what we do, usually they say, okay, don't write the e anymore, deal with this limit, which is limit x ln x. And in my previous lecture, in part 1 of this lecture, you learned how to deal with x ln x. Then at the end, that number, that limit will become the power of e. But usually, we forgot that we have an e there. You just put, for example, you end up, when you do this limit, you end up with 0, and you say, oh, my answer is 0. But no, it's not 0. For example, it's e to the 0, which is different, correct? Then my recommendation to you is to avoid such a mistake, write down this e. It's not that much, right? Write down that e in every single step. Look, you have e, limit, x approaching to 0 from the right, x ln x. If you plug in 0, it gives you 0 times infinity. We did this example in part 1 of the lecture, right? Now, what I do, I'll change this one to quotient. It means I will write e limit of ln x over 1 over x as x approaching to 0 from the right, which is equal. Now it gives you 0 over 0, correct? Or infinity over, sorry, if you plug in 0 here, it gives you infinity over infinity. Now you can apply the L'Hopital's rule for this limit. Then you can write e to the power of limit, the derivative of the numerator, which is the derivative of ln x, is 1 over x. Over the derivative of 1 over x, even I show in one of my examples in previous lecture, gives you negative 1 over x squared as x approaching to 0 from the right. Simplify, it gives you e limit as x approaching to 0 from the right, 1 over x times negative x squared. Cancel out the x, it gives you e to the power of limit as x approaching to 0 from the right, negative x. Plug in 0 here, it gives you e to the power of 0, which is what? 1. Correct? This example is for indeterminate powers. Every time you raise your limit or you write as a e to the power of your limit, and you use ln. Why we are using ln? Because you see, you have f of x to the power of g of x. To bring g of x down from the power, the only way is to have here a ln, right? That's why we are using ln. Let me see if I have another example also for you. Example number 2. This one is a little bit more complicated, but if you are good with trigonometry, it's not that difficult, right? Limit as x approaching to pi over 2 from the left, tan x to the power of cosine x. First thing to do, check, plug in. Tan of pi over 2 gives you what? Tan of pi over 2, the graph of tangent. When you're approaching to pi over 2 from the left, the graph goes to infinity, correct? It gives you infinity. Cosine of pi over 2 is 0. You see, you end up with infinity to the power of 0. Then what to do? Use the E method or ln method, correct? You can rewrite this limit as a e to the power of limit x approaching to pi over 2 from the left, ln tan x to the power of cosine x. Now bring down the cosine here. You can write as the e limit as x approaching to pi over 2 from the left, cosine x ln of tangent x. Correct? If you plug in here now the value of pi over 2, it gives you 0 times infinity. Correct? When it becomes 0 times infinity, you have to change it to quotient. Part 1 of my lecture. You have to change this one to quotient. What I will do this. E limit x approaching to pi over 2 from the left. Keep the ln tan x in the top. Ln of tan x. Move cosine x to denominator. It means you will write 1 over cosine x. Correct? Definitely when you deal with derivatives, you don't like to deal with 1 over cosine. You change it to secant, right? Because right now, you end up with infinity over infinity. If you plug in pi over 2, it gives you infinity over infinity. Now you have to apply the L'Hopital's rule. But before that, instead of cosine x, let me change the color because I want to save a little bit. Here, instead of 1 over cosine x, you can write secant x, right? Because 1 over cosine gives you secant. Now, let's apply the L'Hopital's rule for our limit. Then e to the power of limit as x approaching to pi over 2 from the left. What is the derivative of ln? The derivative of ln u. Remember, I gave you a formula, d over dx of ln u equals 1 over u times du dx, right? Then this one will be 1 over tan x times the derivative of tangent, which gives you secant squared, over the derivative of secant x is secant x tan x, right? Secant x tan x. before moving or before plugging the value, try to simplify this fraction, correct? To simplify this fraction, there are different ways. Look, you can rewrite this one as a limit of e to the limit of x approaching to pi over 2 from the left. Instead of 1 over tan x secant square, you can write secant square x over tan x all over secant x tan x. To simplify more, you can write e limit x approaching to pi over 2 from the left. Now to simplify, I will simplify it in this corner of my board. I will show you how to simplify. I shouldn't show you how to simplify. Each one of you, you can simplify this fraction, but still I will do it here for you. You have secant square over tan x. Here you have secant x tan x over 1 actually. To simplify, you flip it. 1 over secant x tan x. Secant x cancels out with secant x. Then in the top, you have secant x over denominator. Tan x times tan x gives you tan square x. Simplify more. Instead of tan x, you can write sine square over cosine square. And instead of secant x, you can write 1 over cosine. Then 1 over cosine x times, here, tangent means sine square over cosine square. Then flip it, it gives you cosine square x over sine square x. Cosine cancels out with cosine, you end up with 1 over sine square x. Bring that value here. It means e to the power of limit of 1 over sine squared x as x approaching to pi over 2, correct? And also not 1, sorry, I missed, we have a cosine also, cosine x. Cosine x over sine squared x as x approaching to 0. Now, if you plug in pi over 2 here, you end up with e. Cosine of pi over 2 gives you 0 over sine of pi over 2 gives you 1, 1 squared is 1. It means you end up to e to the 0, which is what? 1. I did 2 examples, and by chance, both examples, the answer is 1. Don't think that all the problems you end up with 1. Okay, if I see the power, immediately I'll write the answer 1. No, the answer could be different, correct? Then by chance, in these 2 examples, both answers become 1. This was all about section 6.8. We are done with chapter 6. I will stop the lecture here, and next day I will explain to you chapter 7, and we will start. Chapter 7 is all about the techniques of methods of integration, the methods that you didn't saw yet. You used very simple integrations in calculus 1. But here we give you all methods, most of it in calculus 2, how to integrate a given integral if it's not fitting in your table of integration, correct? In chapter 7, we deal with all those methods. I will stop the lecture here and see you next time for the lecture for chapter 7.